Hi, everyone. Welcome to the HAI weekly seminar. Just a few house rules before we get started. I'm Deep. I'm the Director of Research at HAI. I'll be moderating today's seminar. So what that means is that if you have questions for our speaker, Stefano, please ask those questions on Slido. You can see that on the slide there. You can either point your mobile at that QR code or look in the Zoom chat at some point for the link to that. And the last way to find it is to just go to our hai.stanford.edu website. I'll be watching those and I'll be sort of soliciting questions and curating them for Stefano at the end of his presentation. That's sort of it for house rules. It's my pleasure to introduce you all to Stefano Ermon. Stefano is an assistant professor of computer science in the CS department at Stanford University, where he's affiliated with the AI lab. He's also a fellow of the Woods Institute for the Environment, so his work is truly spanning two very different fields of research in the typical HAI way. His research is centered on techniques for probabilistic modeling of data and is motivated by applications in the emerging field of computational sustainability, which is extremely exciting. He's won several awards, including 4 Best Paper Awards at AAAI, UAI, and CP. He also has an NSF Career Award. He's also an Office of Naval Research and Air Force Office of Scientific Research Young Investigator. He's also has a Sony Faculty Innovation Award, a Hellman Faculty Fellowship, a Microsoft Research Fellowship, a Sloan Fellowship, and the International IGCAI Computers and Thought Award. Stefano earned his PhD in computer science at Cornell University in 2015. And so without further ado, please, Stefano, take it away.
All right, thanks a lot for that kind introduction, and excited to be here and tell you about my research. Can you see the slides?
Yeah.
All right, yeah. So let's jump right in. So what I'm gonna do is I'm gonna tell you about some of the work we've been doing at Stanford on using AI to address sustainability challenges. And this is joint work with several colleagues here at Stanford, in particular David Lobel, Marshall Burke, and also a number of students and postdocs. And this several projects that were done by students in our CS 325B Data for Sustainable Development class, also here at Stanford. Right, so to set the stage a little bit, as you probably know, in the last few years, there's been a lot of progress in artificial intelligence. Many subfields in computer vision, we've been able to build systems that are pretty good at recognizing objects, classifying images, speech recognitions. Our phones are pretty good at recognizing what we're saying, translating between different languages. Advances in reinforcement learning have led to machines that can beat the very best human players at really complex games like Go and chess. So the whole field of AI is booming. Very exciting times to be working in this area, and it's pretty clear to me that these technologies are going to have a massive impact on society, on the economy, pretty much every aspect of our lives. And so what I'm really excited about is thinking about ways to, given all this potential that these technologies have to transform the world and change the world, I've been really thinking about whether there are ways to use these techniques to actually promote the well-being of humanity throughout the world, and essentially make sure that they actually, and these technologies, the amazing technologies that we're developing, actually end up benefiting as many people as possible. So in this context, I think a lot about issues of sustainable development. I think these are the big problems that our society is facing today that we should all be thinking a lot about. And I think these are pretty well summarized by these 17 SDGs from the United Nations. And these are kind of like the big goals that the UN set for the world leaders to try to achieve by 2030. And you see problems like trying to end extreme poverty, hunger, fight climate change, reduce inequalities throughout the world, find sources of affordable and clean energy. I think these are the big challenges, again, that our society is facing today. And what I'm hoping to convince you in this talk is that there are ways to contribute towards this problem with the algorithms, with computational tools that we know of in the computer science department. And we're not going to solve them with an algorithm, but the hope is that we can help providing more quantitative, more data-driven approaches to these really complex and really difficult problems. So one of the reasons these problems are hard, I think, is well summarized by this quote from Kofi Annan, is that we actually understand very little about what's going on, especially in the poorest part of the world. And these data gaps really undermine our ability to target resources, develop policies, track accountability. Without good data, we're flying blind. If you can see it, you can solve it. Right, and so just to be more concrete, let's look at the goal number 1 that you've seen on that list, which is ending extreme poverty by 2030. The way, if you want to solve this problem, you better have a way to measure progress toward this target. And the typical way people collect data on this kind of outcomes is through nationally representative surveys. And surveys are expensive to do. You have to send people on the ground knocking on doors and collect data. It's a very manual process. And as a result, they are not done very frequently. And so we've actually done this, this study in a recent science paper that appeared a few weeks ago, kind of like evaluating, well, how much economic data is available throughout the world in different countries. And so you can see here, each country is color-coded by basically the frequency between 2 consecutive surveys, the average across the world. And you can see that there are many countries that are red or orange, meaning that there could be decades between 2 consecutive surveys in this kind of in certain countries, or there are countries that are black, meaning there is no survey data available at all for those countries. And as you can imagine, with this kind of data, it's very hard to track progress, figure out whether whether the policies that governments are implementing are working or not. It's very hard to track accountability. It's very hard to do social science research if we're trying to understand what are the drivers of the variation that we see on the ground. And kind of like just you can probably see it from the map in a qualitative way, but if you look at the relationship between the amount of survey data available and the GDP per capita, is the one that you would imagine. There is a correlation there, and there is some kind of like negative correlation between the amount of the economic data available and the level of political freedom in this kind of society. So the places where we would need most data, the poorest parts of the world, the less politically free, are the ones where we have the least data available. And this is not just economics surveys. If we look at population censuses or agricultural censuses, again, key inputs in a lot of these problems, these big problems that we're trying to solve. The kind of data that is available today is very scarce. Censuses are done very infrequently. Surveys are also done infrequently, and they even when they're done, they're kind of like sampling the population in a very sparse way, not a representative way, but very sparse way. And so maybe the one way to summarize this is that we have these big problems with very little data. Right? And so one of the things we've been thinking about is whether there are better ways or alternative ways, more scalable ways to collect data on a global scale. And so we've been looking into ways to essentially combine globally available, cheap, passively collected data sources, like from satellites, of phones, crowdsourcing, combine them with recent advances that we've seen in AI and ML to come up with more scalable ways to essentially track the health of our planet in real time, make sure that we understand what's going on all over the world, and hopefully use this data to inform policies, to inform research in the social sciences, and so forth. So in particular, in this talk, I'm going to focus on satellites. The last decade or so, there's been enormous progress in the kind of quality and quantity of the data that has become available. This is the kind of image of that you could get from space about 10 years ago. Here you can see that the image is very pixelated. Every pixel corresponds to an area of 30 meters by 30 meters. And so kind of like this data is very useful, but you cannot really see much about what's going on the ground. These days, it's very easy to get higher resolution data. This is a 3 meter by 3 meter kind of resolution image of the same area. These kind of images are available today pretty much everywhere in the world. They are updated very frequently. Like you can get an image of this resolution for every location in the world, updated every day, right? So You can even get higher resolution images. These are updated less frequently, but you can get sub-meter resolution images where you can start to see all kinds of aspects of the economy. You can see cars, you can see containers, you can see agricultural fields, you can see how the environment is changing on the ground. And so the promise here is that perhaps there is a way to fill this data gap, combining these new sources of data that are cheap, they're plentiful, they're available everywhere, with machine learning to come up with more scalable ways to understand what's going on the ground. Right? And so we recently did this analysis where we kind of like looked at, well, if you take a random household, let's say somewhere in Africa, and you check how frequently will this household show up in one of these nationally representative surveys that people do. And given the frequency at which surveys are done today, a typical household will show up in one of these surveys maybe once every 1,000 years, right? Because they're done very infrequently, and whenever they are done, they sample very few households in a country. And even in the US, a typical household will show up in one of these surveys maybe once every 10 years, roughly. On the other hand, if we look at the frequency at which a typical household will show up in one of these satellite images, we see that that might be once every week, once a month, something like that. So there's several orders of magnitude difference here. And if we could figure out a way to extract useful information from these images, of course, it's not the same as knocking on a door and interviewing people, but if we can somehow figure out a way to extract information from these images in an automated way, that could really be transformative in the way we measure economic situations and socioeconomic outcomes of various kinds on the ground. And so that's kind of like what we've been looking at. In a few years ago, we started by looking at poverty, just because that's kind of like SDG #1, and it's kind of like a key input towards that goal is kind of like understanding how many poor people are there, where do they live, is the number changing over time. And so we try to see to what extent it's possible to build such a machine that essentially will take as input high resolution satellite images, which are available everywhere, updated frequently. And as we've seen, they contain a lot of information about what's going on the ground, and whether it's possible to process them using recent advances in computer vision and machine learning to come up with estimates of socioeconomic indicators of interest on the ground. And this is promising. However, it's not too easy to do, because although we have a lot of images, there are very few labels. That's precisely the reason we want to build these models, because we don't have a whole lot of information about what's going on the ground. We have some survey data, but it's sparse. It's not done very frequently. Even when you have a survey, it might cover a few hundred, a few thousand kind of enumeration areas across the country. And so we just cannot just take the state-of-the-art deep neural network and train it end-to-end to go from the inputs to the outputs of interest. And so a lot of the research that we've been doing has been around figuring out ways to get around this data scarcity and build systems that can predict these outcomes of interest using less labeled data. So one of the things that we've been looking into is exploiting different modalities and kind of trying to look at co-occurrence statistics between different kinds of data modalities that are also sort of like geolocated and available globally. One such example is night lights. So it turns out that we have satellites that take images of the Earth not only during day but also during night. And here you can see an image of the Earth from space as seen during night. And maybe I'll let you look at this image for a little bit and try to see if you can guess where this is. This is somewhere in East Asia. You can see actually this is South Korea. The one above there is China. And this thing that looks like a island here, it's actually North Korea, right? So you can see that there is a huge kind of difference in the kind of like amount of nighttime light intensity that you see, and we might think that that is somewhat correlated with the level of economic development. And so the idea is that because we have both images of the Earth taken during day and night for essentially any location in the world, we can use this to essentially set up some kind of self-supervised learning problem to teach a neural network to identify useful features without actually having to provide labels ourselves. And so the basic idea is that if I ask a neural network to decide, I give you two images, tell me which one is going to be brighter at night, you can probably guess that the one on the left is going to be brighter at night than the one on the right. And the way you do it as a human is, well, you see that there are cars, you see that there are buildings, traffic. While on the other hand, the other area looks pretty rural. And so the idea is that we can set up this fake learning problem where we're going to ask a neural network to classify images, daytime images, and try to guess what is the amount of nighttime light intensity that you're going to see for that location. This is like a problem for which we can essentially generate a training set as big as we want because we have images from all over the world. And that this is kind of like the regime where deep neural networks tend to work very well. And the hope is that by learning how to guess basically the amount of nighttime light intensity, again, the model will do something similar to what we are doing. It will do that by identifying features like traffic, like buildings. And once we've trained the model to identify these kind of features, hopefully we can then use this pre-trained model that is good at identifying buildings and cars and stuff like that. And then we can use these kind of visual features to try to regress, try to predict other indicators of interest like poverty or population density or other things. And indeed, it turns out that by trying to solve this problem of predicting nighttime light intensity, the model ends up recognizing things like roads, like water bodies, like traffic roads, like tall buildings with shadows. My favorite one is the swimming pool filter. So that the model figured out without ever telling the model, okay, this is a swimming pool, look for this, this is a useful feature to look for. Just by trying to predict nighttime light intensity, the model figured out that, okay, there is this thing that is blue and roundish, and that is a useful feature for predicting nighttime light intensity, and we recognize it as a swimming pool, and we are effectively, without actually having to label any image ourselves, we've been able to train a neural network that is able to identify all these kind of thousands of different features that are useful for predicting nighttime light intensity, and then hopefully we can then also use to predict other economic indicators of interest. Another similar strategy that we've used is to leverage crowdsourced data sets, in particular Wikipedia. It turns out that a lot of Wikipedia articles are geolocated. Now, there is this box on the bottom right where Wikipedia will tell you what is the coordinate of the entity that is being described in the article, like in this case, the Nelson Mandela Bridge. And the idea is that we can now, again, try to use Wikipedia as a source of supervision for a deep neural network. And so what we can do is, again, it turns out that there is a lot of articles that are actually geolocated. This is a map that we produce where we basically plot each dot here corresponds to a Wikipedia article, an English article that is geolocated. And it's a pretty cool map. There are hundreds of thousands, millions of articles that are actually geolocated. And as you can see, this is pretty cool because we never actually overlaid the shape of the continents on this map. That actually arises automatically just because people write articles about things that are, I guess, next to them, next to where people live. And so this shape of the continents actually emerges automatically just if you just plot the locations of existing geolocated Wikipedia articles. But kind of like the takeaway is that there is a lot of them and they're not included in developing countries. And so what we can do is we can now, because these Wikipedia articles are geolocated, what we can do is we can acquire the corresponding satellite image of that location. Let's say the Nelson Mandela Bridge, we can acquire a satellite image of that bridge. And then you can think of the Wikipedia article as being a very detailed caption for the high resolution image. And then the idea is that we can train, again, like in the same spirit as the night and light prediction task, we can train a neural network to predict properties of the Wikipedia article from the satellite image. And by doing so, the model needs to figure out, it needs to recognize different visual features, it needs to figure out how to interpret a satellite image. And again, this is kind of like a situation where we don't have to provide any manual labels because we have this automatic pairing between articles and images, and we can construct this automatically. We can generate a huge training set, and we can use this as a pre-training strategy to learn how to interpret satellite images without actually having to provide any labels. It turns out that this strategy is very helpful. Again, kind of like you can learn how to recognize different kinds of buildings, different kinds of features that are visible in the images. And hopefully we can then transfer this knowledge that we've acquired by trying to guess properties of the Wikipedia articles from the images for other tasks that we care about. Maybe let me skip this. There's also other kind of like unsupervised ways of approaching this problem that we've explored, but sort of like back to the original problem. The idea is that once we've used one of the strategies to essentially pre-train a neural network to identify visual features in images, what we can do is we can now start to attack the original problem, which was how do we predict, let's say, poverty across large geographies using satellite images. And so the pipeline then is as follows. We have a small number of locations for which we have survey data available, let's say from the World Bank or from the National Statistics offices. And what we can do is, again, we can acquire satellite images for these locations, and we can process them using one of these pre-trained models so that we can extract these kind of rich visual features, like is there a swimming pool there, are there buildings, are there roads, and all these kind of things. And then what we can do is we can look at the survey variables of interest, like how many poor people are there, what kind of assets people own, what is the consumption level of the population in that, let's say, in that village. And we can try to see to what extent we can regress, we can predict these survey variables of interest using these visual features that we can extract from the satellite images. And the idea is that once we've trained this model, then we can sort of like scale it up and we can apply it over very large geographies. We can make predictions in locations where we don't have any survey data that has not been collected. And we can even try to apply it in countries where no survey data is available at all. We can kind of like try to train the model on countries in which we have survey data, and then we can try to make predictions in countries where there is no survey data available at all. And by doing this, we've been able to scale this up over the whole African continent. So now you can basically pick any country of interest, and we can tell you, let's say, different districts, how, on average, what is the distribution of asset wealth, which is kind of like a common indicator that is used in development economics, that is kind of like capturing ownership of different assets, like how big the houses are, do they own a TV, a fridge, a car, a motorcycle, things like that. And we can see the spatial distribution of wealth, across different countries, within a country, let's say at the district level. We can even zoom in all the way to individual villages. And we can check how things are changing over time because images come in all the time, and we can try to make predictions at a given time slice and then at a future time slice, and we can check how things are changing on the ground. And we can do that in a very inexpensive way, because once the model has been trained, the only input that we need are images, and so that's pretty inexpensive. And you see some of the kind of things that come out from this model. Here you can see the difference between Ghana and Ivory Coast. You can see that one country is kind of like hasn't changed at all in the roughly decade from 2003 to 2018, while the other one has experienced a huge growth, and it's kind of like consistent with the fact that there was a civil war and a pretty difficult situation over those years. And so even though the model was able to pick that up, even though it had no notion of civil wars or no knowledge of this, was able to entirely figure this out just by looking at satellite images. And so we've done this over many countries in Africa. We've collected all the survey data that was available there, and we've evaluated the performance of our model. And it turns out that it's very accurate. Kind of like at the village level, we get the R-squares of around 0.6, 0.7, meaning that we can explain 60–70% of the variation that you see on the ground just by looking at satellite images. At the district levels, if you're willing to zoom out a little bit and kind of like produce average over larger areas, the R-squares are even higher, maybe 0.75, 0.80, something like that. And we actually think that this is quite good. As a thought experiment, we try to see what is the correlation between different surveys when they are available for the same country. Sometimes there is a survey done by the World Bank and one done by a national statistics office for the same country in the same year, and then you can check how correlated are those two things. And the correlation is about 0.8. The R-square is about 0.8, which is kind of like in the ballpark of the sort of numbers that we get when we look at the correlation between our predictions from space and the measurements that are available, which are affected by noise because, of course, there's measurement error. You just need to, you're sending people on the ground, and inevitably, even the ground truth is affected by error. And so we would never expect perfect correlation between our predictions and the ground truth, because that's also affected by error. So this is exciting. It really is providing a new way to look at poverty across very large geographies that is enabled by advances in AI and computer science. It's relatively inexpensive in the sense that the only thing that we need are images, and once the model has been trained, you can just feed them in and you can keep these maps updated in a relatively inexpensive way. It is, however, a pretty massive kind of amount of computation that we need to do to produce this sort of maps. Even if you look at a single country like Kenya, it's about 10 billion pixels that you would need to process in medium resolution, several trillion pixels that you would have to process if you were to look at every location in Kenya in high resolution. And so we've been looking into ways to make this more scalable by essentially training AI, reinforcement learning, and AI agent to essentially figure out adaptively what kind of data to acquire automatically in order to make the prediction that it needs to make. The idea is that there is a lot of areas, a lot of locations where nobody lives, and there is no need to acquire high resolution images for those areas. We really need to acquire high resolution images in areas where people live, where the model is uncertain about the kind of predictions that it should make for that area. And so what we've done is we've trained essentially an agent that will automatically learn basically where to zoom in, where to acquire high resolution images automatically. And so, instead of acquiring an image down here where there is nothing, it might learn that it's better to acquire high resolution images up here where people actually live and there are buildings, and maybe you can see cars and other things that would be helpful for coming up with an estimate of economic development. So basically, we've trained a reinforcement learning agent that learns when to zoom, when it's necessary to actually acquire high resolution images, or when it's fine to just use low resolution one, and where to zoom, and kind of like figure out, okay, I see this, I can get a sense that there is a city here, I should probably get a few high resolution images, I should zoom in a little bit to see what's going on the ground to try to maximize my accuracy, while at the same time trying to minimize the computational budget, try to minimize the number of high resolution images that we have to acquire. And sort of the model automatically learns this trade-off by trying to maximize accuracy while minimizing cost. And so intuitively what happens is that, you might see this medium resolution image, and then you figure out, okay, this is a good area to zoom in, and then you acquire the high resolution image, and then you, let's say, do object counts, you figure out what kind of objects are there on the ground, you count different things, and you use them to make the final prediction. And by doing this, we basically have a negligible drop in accuracy, but we can drastically reduce by, let's say, 1 order of magnitude, the number of high resolution images that are needed to come up with that estimate. So that's one of the ways we've come up with to try to make this pretty massive computation more scalable. Moving on, we've also been looking at different kinds of outcomes that we can also measure from space, in particular the ones related to food security. So we've been looking at agricultural outcomes, and we've been trying to build systems that can kind of understand agricultural productivity, again, across wide regions in an inexpensive way by essentially processing satellite images using advances in ML and computer vision. Food security is still a problem. You can see from this graph that kind of like the situation was getting better and better, but then now it's kind of like, again, getting worse across the world. And we've been looking at to what extent we can use remote sensing data to essentially understand agricultural productivity, which is kind of like a key input in a lot of food insecurity measures. And again, we basically built a system that can take images of the Earth taken from space over time and can use it to essentially predict, to try to identify cropland, identify what crops are being grown, and even guess basically how productive the crops are. This is, I guess it's unfortunately, it's not showing. It's supposed to be a video, but it's not showing up. Or maybe it is. This is a demo of the system in the US, where we're basically looking at soybean and kind of predicting from space how productive different counties are in the Midwest. And it turns out that we can be very accurate. We can come up with forecasts that are almost as accurate as the one that the USDA is able to provide. But our system is, we can do it from space. They actually have to collect samples on the ground, call farmers, things like that. And what this means is that we can actually apply our system in geographies where no data is available or very little data is available. This is a demo of the same system in Kenya, where we're looking at maize yields. And again, it's a similar thing as before. Here we're looking at how across Kenya, how different regions differ in terms of how productive cornfields are. And you can do it at the state level, you can do it at the district level, and you can zoom in again all the way to the level of individual fields. And you can kind of look at, okay, here red fields are productive. They have a higher yield in terms of tons per hectare. Blue fields are less productive, and you can zoom in at the level. Each of these areas here corresponds to an individual smallholder farm, and we can actually get a sense of, okay, which farms are being productive, which ones aren't. Sort of like key inputs if you're thinking about how climate change is affecting productivity, whether interventions are working, what kind of interventions are better if we're trying to increase yields and improve food security and feed a growing population. So lots of potentially very useful inputs for a lot of policy decisions that could come from this kind of estimates. We've looked at a number of other things that we can see from space. One is infrastructure quality access, like do people have access to electricity or not? When did they get access to electricity? Again, it turns out that we can do pretty well by essentially training a machine learning model based on the available survey data, and then extend it to geographies and locations for which maybe no survey data is available at all. And we can come up with these very comprehensive maps that will tell us, what is the quality of the infrastructure that people have access to, which is again, potentially very useful input for research and for policy decisions. And there's a number of other things that we've explored. We can estimate population density, try to count tents in refugee camps. We have an upcoming paper on where we've been able to count all brick kilns in Bangladesh. It's like a highly polluting kind of economic activity. And we've been able to build a comprehensive map of where all the brick kilns are and where they are located. Are they in compliance with environmental laws? Are they too close to schools? how are the numbers changing over time, all kinds of interesting analysis that this is a collaboration with people in the med school that would not have been possible without this kind of like comprehensive data that we can collect at scale using data and machine learning. Final thing I'll mention is that we are not just restricted to satellite images. We've also been exploring other kinds of widely available data sets that contain information about what's going on the ground. One thing that we've started looking into recently is basically street level imagery. I think Google Street View, except Google Street View is not globally available. It's only available in select countries. It's very high quality, but it's not globally available. There is an alternative called Mapillary, which is actually crowdsourced. And so it's available all over the world. And the quality is lower compared to Google Street View, is that there's a lot less quality control, but still you can see from these sample images here, these are basically images taken on the road through dash cams and GoPros and stuff like that. And they contain a lot of information about what's going on the ground, about infrastructure, about economic activity, about people. And so we started processing this sort of images. We have a recent paper where we've done this work in India, where we looked at all the mapillary data that is available there, process all these images, identify different kinds of objects that you can see in the images, and started to look into to what extent can you predict socioeconomic indicators that people care about and that people typically measure using surveys or censuses from the images. To what extent can you predict population levels? Can you predict sort of some notion of asset wealth or poverty? Even we've been able to do a reasonably good job at predicting health outcomes related to malnutrition. And so we're pretty excited about this idea of potentially combining images taken from space and images taken from the ground. There's of course going to be things that you cannot see from space. You cannot see, the resolution is always going to be limited, but perhaps you can complement it with images taken from the ground, and that might help come up with an even more accurate picture about the situation on the ground. And yeah, I think, this is, I guess I had 40 minutes, and so I have 2 more minutes, and I'll give you the final pitch. The final vision is, clearly we are facing some pretty formidable challenges towards sustainable development, very big problems like hunger, poverty, climate change. These are very difficult problems. They affect all of us in different ways. The scale of these problems and the complexity is just hard to even grasp, and I'm fully aware that we're not going to solve them with an algorithm, but hopefully I gave you a sense that there are things we can contribute. I think perhaps the lowest hanging fruit is just filling the data gaps that we see in the space. I fully agree with Kofi Annan's quote at the beginning that if you cannot measure things, you cannot measure progress, you cannot figure out what's working, what's not, and we really need more data-driven decision making, data-driven resource allocation, data-driven policy making for a lot of these problems. And I think that's certainly an aspect where we can help with new data and new techniques for processing the data and extract actionable insights from this, from images, from crowdsourced data, from phones, from social media data. And I think it's certainly doable. And I think that's kind of like my vision for the next few years, to be able to build a system that can really track the health of our planet in real time. I think we're there from the perspective of the data that is available. It's just a matter of developing the AI and the ML tools on top of that can do that at scale, that can really process these massive amounts of data and extract the things that we care about. And I think that's going to be a key. It's going to be very, very useful in terms of informing policy and research in the social sciences. And if you're interested in working on these kind of problems, please reach out to me. We also, if you're a student, we have a class on data for sustainable development, where we collaborate with people on campus that have interesting data sets, interesting problems, and then we try to see whether it's a class-based project, or we try to develop AI ML tools to help, often trying to predict something from satellite images or from street view images. A lot of the projects and the topics I described, or many of them, are actually started as class projects in that CS 325B. So if you're interested, please take that class. And yeah, of course, this is joint work with a lot of students and David Lobo, Marshall Burke, and I think that's about it. And I'm happy to take questions.
Oh, thanks, Stefano, for the wonderful talk. There's several really interesting threads in the chat. I'm sort of estimating 4 principal axes. So one is about technical questions about like kind of the training. Another is about sort of uses, like how practical are these machine systems for governments and policymakers. Another round of questions is about possible confounds when you do this kind of work in the data. And the last is sort of like kind of concerns about potential ethical challenges in dealing with these data in developing countries. So how about we start with the technical and then sort of go down the list there. We can start where I'm at least personally most comfortable. So I think the first sort of class of questions is really based on the way you framed your starting talk with the Kofi Annan quote, which says that essentially that data gaps undermine our ability to target resources, and without good data, we're flying blind. And the way you start the talk is like, well, what kind of data is currently being used to address the UN Sustainable Development Goals? And it's typically survey data. The issue with survey data is that it's lacks in spatial resolution and also temporal resolution. By temporal resolution, I mean frequency at which surveys are administered. And then you present a solution, which is satellite imagery data, which is, of course, much higher spatial resolution. And apparently, I'm learning from your talk, higher frequency of refreshing the actual data set. But then you also say we still lack data, which is in the labels, which if you want to do classic sort of supervised learning, things get a little bit hairy. But I think it's okay. I just want to kind of, it struck me that like you're still missing that data. And the solution you presented was taking sort of self-supervised approaches to learning features. One was sort of predicting the nighttime intensities from the daylight images. Another one was sort of using the Wikipedia entries as captions to describe satellite imagery data. And from these, you can extract features which allow you to then predict labels from surveys. So my first question there is like, did I get that right? I think there were a lot of questions like, well, how does this actually work? And that was my sense.
That's perfect. Yeah, perfect summary.
Uh-oh. Okay, that was easier than I thought. So let me push you a little bit further then. So another way one could do this is saying this sort of self-supervision is still difficult. Like I still have to frame up a problem like the two I just described. Like let's pick on the night versus light imagery. You know, I imagine there might be a registration issue in the satellite imagery taken in the daytime versus the nighttime if you're doing a pixel to pixel prediction, or at the very least, some way of quantifying illumination levels. I think you were solving it as a classification problem. So I'm just kind of curious, and pardon my naivety, have you tried the even dumber thing, which is just taking features extracted from a pre-trained convolutional neural network, even though it might have been trained on data that are not remote sensing data?
Yeah, so that's indeed something we do, and we actually often start from that and then fine tune on one of these self-supervised learning tasks. They don't tend to work very well. Like ImageNet trained network don't do particularly well, like on remote sensing data, because they are so different. And the other challenge that I didn't quite talk about is that you often have multiple bands. So unlike kind of like traditional images that we're used to working with in computer vision, is that this is not just visible bands. You might have infrared, you might have radar, you might have temperature. And so we don't know what kind of filters are good for those sort of features. And so that's another challenge, that we don't even know how to initialize those layers of using traditional computer vision pre-training strategies.
Oh, I see. So it's a mixture of like sort of input data distribution shift when dealing with pixels, but also different kinds of data that are not necessarily reflected in ImageNet. Is that right?
If you think about the image analytic, like it's very object centric. Right? There's a big object in the middle, and this image
Yeah.
is nothing like it. Like the scale of the object is very different. There's small stuff, big stuff, and they are spread all over, and so it is quite different.
Interesting. Okay, thank you. That's super helpful. There's a couple of questions going down the sort of the technical rabbit hole. The other thing that struck me that you showed were some preliminary results where you say, okay, I've learned some features using a self-supervised method. And then you showed that there were detectors that do things like detect swimming pools. And so my question is like, how do you extract that from the features in a systematic way? Is it important to do so? What are some other surprising or unsurprising things you found that are useful in predicting?
Yeah, so
variables of interest?
that was honestly a little bit cherry picked, and the students spent a lot of time trying to sort of like look through the activations and see where something meaningful came out of it. There are thousands of other features that, I mean, as you know, interpretability is pretty challenging, and we just kind of like wanted to convince ourselves that these models were doing something reasonable. Because I mean, we know we could certainly evaluate end to end how accurately they predict, and we were pretty convinced that they are doing a good job. But then if you want to sell this to policymakers or even other researchers, they always want to know, but why, how does this work? How can you open up the black box for us? So that's what kind of motivated this, well, let's try to get a sense of what sort of features these models are actually looking for. Actually, recently we've actually just tried to do straight object detection instead of just training end to end with these features that we don't know what they might be. So there have been recently big data sets that have been developed for object detection in satellite images. And so you can kind of pre-train on one of those and then try to see to what extent object counts from a pre-trained detector can be used for estimating these indicators. And it doesn't do as well as the end-to-end things that I talked about, but it's much more interpretable, because at that point you say, okay, I've counted this many cars, these many buildings, these many boats, these things, and then I regress based on counts. And I know exactly what the model is doing, which is something policymakers and end users appreciate a lot, and they'd rather give up a little bit of our square if they understand how the model is working.
That makes a lot of sense. And then there's also a question from the audience that's sort of related to this. Is there any way to sort of easily get the pre-trained models for remote sensing data to then tailor those to other sort of challenges related to the UN SDGs?
So we make our models available, and so we have GitHubs and things. I don't think there is an ImageNet pre-trained model that anybody can just use and plug in. It's actually something I've been thinking about. I've been trying to develop, but the use cases are so varied that it's hard to. And I guess the field is also a little bit newer, and there is not we don't have. I mean, there are some challenges that people have set up where, you know, a lot of people compete and try to build the best models they can, but I think it's still early stages. But I think that would be a very impactful kind of thing of having like a single big pre-trained model that then you can fine tune on a lot of different things. I think that'd be quite helpful.
It's like the UN Sustainable Development pre-trained Stefano model. Like, another last technical question, we can move on to the more interesting questions. This one's about validation. So let's say you're predicting survey results from features that you've learned, and to measure sort of R-square, of course, you have a training set, you have a test set, and then the question is about the validation set. So maybe you're predicting a survey result where there was no data. Have there been efforts to then go and actually collect that data on the ground to really test out of bag prediction?
We haven't, but we have done. I mean, the way the R-squares that I reported are always out of samples. So we do, they are on held out data. And so we are fairly confident that those should reflect roughly the kind of performance you might expect when you try to predict at a location that you haven't seen before. We've also tried harder kind of generalization things like out of country, where you could do sort of like leave one country out cross-validation, where you try to train on a bunch of countries and then you predict in a country that you pretend you don't have data for that country, and you try to predict how well, and you check how well you would have done. Because that's kind of like the gap. When we try to make predictions in Somalia, there's no data there. So we want to have a sense of how well can we expect these predictions to do, and the closest we can get to is to do this kind of thought experiment where we pretend we don't do it for a country and see how well it would work.
Got it.
So yeah, we haven't actually collected data, but we what happened? But we believe. Okay, so what? Okay, sorry.
No worries.
Yeah, they're fairly accurate estimates based on the R squares.
Got it. Okay, so moving on to sort of the confounds series of questions. So there's a question from the audience was like, sustainability is a matter of critical importance, but there's a complicated relationship to other issues like poverty. So for example, in the lighting case or the illumination case, there's confounds with the growth of exploitative technology. For example, there's a lot of illumination around oil fields. Or, you know, in Nigeria, the illegal sort of refining of oil is associated with fires in the evening, which could, of course, confound predictions of economic development. So how do you, and I think there's a second question that sort of builds up on that, which is related, but not super related. So this is a question that's somewhat interesting. As you know, Germany has existed in two parts for a long time, or did. And this has affected many variables from building structures to lighting voltages. And so you could imagine trying to model that in, although that's the best way to like kind of rule out confounds, is to take them into account. So how have you handled these types of confounds in your work?
Yeah, so I mean, that's a good point. Like, for example, I mean, an even simpler approach could be, why don't you just try to make prediction just using night lights? And people had done that before, but it tends to not work very well because of the reasons you just said, but also because there is many villages that are completely dark at night, but there's still a huge variation in terms of how rich or poor they are, and there's no way to distinguish them just by looking at night lights because they are completely dark because they don't have electricity. And so that's exactly the reason we decided to let's look at daytime images, because there's a lot more that you can see in a daytime image. There's a lot more information there, and it's just a matter of trying to get the right features that then we can use for predicting these indicators. And but indeed, I mean, there are limits to what you can do because you cannot see inside people's houses, and thankfully, and so there will always be things that you cannot measure from space. But we think, and the model will make mistakes. I mean, as you've seen, the estimates are not perfect, so it's definitely over predicting somewhere, it's under predicting somewhere else. And there will always be mistakes, but we think it's pretty good. And it has, again, kind of like the errors that we make are comparable to the ones you would get if you were to compare two different surveys, traditional surveys that are done in the same country. So we're pretty close to really good data, I think, that people could start using for making decisions.
Yeah, that's a good point. If you're as good as the inner reliability across surveys in the same field, that's sort of a good baseline.
Not too far, like we're not there, but it's not too far. I mean, if you there are squares, they're pretty comparable. So it should be pretty good. I think I'm pretty confident this data should be valuable and useful.
Got it. And then there's another question for the audience, which is like, how do you ascribe confidence intervals to your predictions, if at all, if folks are expected to sort of make policy decisions based on the output of a model? How should they reason about the sense of model uncertainty?
Yeah, so that's something I haven't talked about, but that's indeed on the technical side of things. That's one of the threads that we're working on in terms of calibration, ensuring these models are calibrated. So so that basically kind of like try to get to a stage where the model knows what it knows and it knows what it doesn't know. So it's a hard problem, and there are technical issues that I think people had not considered before that we've been exploring, like stronger notions of like even calibration is just a property that holds on average. And that's not quite what you want, because it could still be the case that the model is under predicting on the poorest part of the population and over predicting on on average it balances, but that's obviously not what you want if you think about using these estimates to allocate aid, that's not the kind of calibration that you want. So we've been thinking about stronger notions of calibration that are more tied to the kind of decision making people will do downstream. So if you know that people will use these predictions to allocate aid based on some, let's say, threshold rules, then we've found that there are other notions of calibration, stronger notion of calibrations that you can impose on your models, so that in some sense there will be no surprises, and the performance that decision makers will get when they use the estimates will match the estimated performance. So there is certainly a lot of technical work that we've done that I didn't talk about in this talk, but reach out to me if you're interested. I'm happy to send you some papers on some of the work we've been doing there. And it's definitely a topic that is very important: calibration and uncertainty estimates, and there's a lot more work to be done in that space.
Got it. Okay, so yeah, I kind of popped back up to the technical side of things. So going back to the uses, I think to summarize a group of questions from the audience here, it's to what extent have private organizations or governmental agencies either inquired about your work, the predictions? To what extent have they sort of actually used sort of the ideas you've expressed here to create and implement policies?
Yeah, so what happened is, after we published these papers, we got a lot of interest from a lot of from small NGOs to big organizations like World Bank. One thing I didn't mention is that so based on all this interest, we actually started a company, like a startup. It's called Atlas AI, where we've been essentially scaling up these technologies, and we've developed products that people can use. And so a lot of the efforts in terms of getting this data out to decision makers happened at the company. But yeah, I mean, we have World Bank as customers, like lots of big organizations that are using the data. So there's definitely been a lot of pickup in terms of organizations, users that are kind of like starting to leverage this data.
Excellent. I did not know that. That's very, very cool. Okay, so maybe in the last 2 minutes, I'll give you the the most upvoted question, which is a tough one, which are there any ethics of AI related challenges you foresee in these algorithms? And a subsequent question that might be related is, have you encountered concerns about surveillance and or quote unquote data colonialism, especially given the fraught history of extracting digital as well as natural resources from underdeveloped countries?
Yeah, I mean, I guess you could imagine that if people were to use these systems to allocate aid or make policy decisions, like you could imagine all kinds of adversarial attacks, or you can imagine people exploiting the systems. And then once you figure out what kind of features force the model to make a certain prediction, you could try to attack the system. So there's certainly those kind of concerns. Other kinds of concerns are simply that there's a lot of things you can see from space, and people might use this data in ways that we have not anticipated. Like I know, like land property ownership is a big issue in many African countries, and so if you have yield estimates, you can figure out which areas are yielding a lot and which ones are. Like there could be unintended consequences that we are somewhat concerned about, and so that's one of the reasons we don't actually provide the highest resolution data to anybody. Like you have to actually sign up, and you have to sign some sort of like agreement to try to prevent some of those misuse. But yeah, I mean, as any other technology, I think there could be malicious uses that we haven't thought about. Of course, we're trying to do it for good, but there could be potentially misuse of these kind of techniques.
Right. Yeah, that's a tough set of issues to handle. Okay, well, we're at the top of the hour. Stefano, thank you so much for giving this wonderful talk. And thank you to the audience for tuning in. We will see you next week. Yeah, thank you. I'll see you on the other side, Stefano.
Thank you.